Right, we're gonna start. So welcome to the Swedish NLP Seminar. This is something that we organize here from Sweden with support from RISE also. And we do this every second week, Wednesdays of course, this time. And as you can see, we do this as a hybrid seminar, so we have people joining online, quite a few today. And we also have the physical space here in Stockholm. We also have a physical space in Gothenburg at our Gothenburg office. You can't see them here now, but they are there and they're starting to take a seat. And this is on selected dates. So if you happen to be in Gothenburg and you want to join the seminar, check our website if we actually have a physical space there at that. Right, so we try to select topics that we think are interesting for the NLP community in Sweden, but of course also for us. And today we are going to talk about our favorite topic, which is large language models. And not just any large language model, but actually our large language model. And I'm going to share my screen now. And I guess all of you know what this is called. It's called GPT-SW3. And today we're going to hear from the people who have actually built the model. So we have Ariel, Ekgren and Amaru, Cuba, Gyllensten, who will talk about the actual technical work on building this model and maybe also evaluating it. But I want to start and just provide some context for why we build this model and also take the opportunity to correct a few misconceptions that I have seen floating around out there in the ether. So this is something that we do in the natural language understanding research group here at AI Sweden. It's something that we started about 1.5 years ago. And we started this research group with the sole intention to just focus on large language models. So everything that we do in this research group is in some way connected to large language models. And GPT-SW3 is of course the first model that we have been working on. It will probably not be the last, but it's the first one. For those of you who have already read the technical report for GPT-4, you might have noticed how many people have been involved in that model. We're this team, so it's quite a small team to build a large language model. But of course, the way that we try to approach this is to form partnerships and collaborations with other organizations and people that think that this is a great idea and that we should collaborate on this. So we work together with RISE and especially Evie and Fredrik Karlsson, who I guess is not here today. They have been heavily involved in the core technical work on GPT-SW3. We also work together with, or actually we are a part of the research arena for media and language, which is one of the WASP research arenas. And through them, and especially Johanna Björklund, we get access to Berzelius, where we train our models, and I guess we will talk more about Berzelius later on. And at Berzelius then, Berzelius is based in Linköping at the National Supercomputer Center, and we get a lot of support and help from them, especially Johan Raber, who is taking care of Berzelius and really helpful for us. So big kudos to him. And also, last but not least, we get a lot of support from NVIDIA, and especially Zenodia Sharpie has been invaluable to get things to run smoothly on Berzelius, and I guess you'll talk a lot about that soon. We also try to sort of build a bigger community around AI and the things that we do. And I know that many of you are part of the Discord already. If you're not, join it. And we try to build a community and share things, maybe get collaborations going. Maybe for the next step of our development, we will try to be more community driven. We'll see. But this is sort of the context that we try to operate in. But of course, we have a lot of organizations here. There's a lot of investment going into actually building GPT-SW3. But just some clarifications. If you read media right now, GPT is all the hype, and there are some misconceptions floating around there. So GPT-SW3 is built here at AI Sweden by the Natural Language Understanding Research Group, and especially the gentleman that you will meet soon. Keep in mind that this is a research project. We're not developing a product here. So we do this in order to do research on large language models. So we do research on the training aspects of this, for example, with regards to scaling behavior and scaling laws. We do research on applications and ways to refine and modify the models. And we also want to validate whether these models can actually be useful here in Sweden, a native Swedish model. So this is not a product, it's a research project, okay? We hope to eventually get to a point where we can release our models completely openly, and then you can build products on the models. But that's not what we do, right? And also then, it's not a product, it's a research project, so it's not a competitor to any other model. It's not a competitor to ChatGPT, it's not a competitor or Sweden's answer to GPT-4. There are lots of differences between these models, and I'm guessing Ariel will go into some of these differences in sufficient detail. So keep this in mind, and if you see things that says otherwise, you know that this is the thing that you should keep in mind. And now I'm going to introduce Amaru, who's a PhD in computational linguistics, machine learning, natural language processing, expert in everything that has to do with transformers, language models, and in particular GPT-SW3. So please go ahead.
So yes, as Magnus have said, I've been quite heavily involved in the technical aspects of training GPT-SW3, and I will talk about quite a bit of that. There will be a bit of numbers, a bit of flop calculations, memory requirements, etc. But I'm going to start with the most important thing, which is data. Swedish is a fairly small language. I mean, not a very small language, but fairly small. But there are quite a few other similarly sized languages that are very close to Swedish, like Norwegian and Danish and Icelandic. So when we started this project, we thought, why not pool these data resources together? So that's why we decided to kind of build the Nordic pile, which is the data that we've trained the model on. And that is a data set which consists of all the Nordic languages, Swedish, Norwegian, Danish, Icelandic, and English, and code. The reason to include English was partially opportunistic. There is a lot of English data available. There's a lot of high quality English data available, but also like in a Nordic setting, English is a heavily used language. A model that does not have the English capabilities would probably not be very useful. Similarly, for code, we have seen some indications that, for example, language models that have been trained on code are better at following instructions, because code has this very formulaic format, etc. And we also thought it would be very interesting to train a model with code. And the Nordic pile, it's based on existing corpora and open sources. So kind of like the guiding principles when we created this data set was that, well, we want quality data, and by quality data, we mean like naturally occurring text generated by humans in a human readable format from many various domains. So that kind of, if, for example, you just scrape the internet, quite a sizable amount of that data would be automatically generated ads. You would have a lot of HTML and other artifacts, and we kind of want to get rid of that. But also, we want to have lots of data. And so quality in terms of, so when I speak of quality, I do not mean necessarily grammatically correct. I do not mean unbiased. I do not mean these kinds of things. I mean, I want text that has been written for by humans for humans with some kind of communicative intent. And well, the whole process of this data set, I mean, like first you start out with data collection and formatting. We do some kind of normalization, quality filtering, deduplication, and weighting of data sources. and then train the tokenizer, yada, yada, yada. And I will go a bit into detail about in all of these. So the data collection process is essentially, we took existing data sets. So Oscar, MC4, the pile, other corpus, most of these are based on Common Crawl. So data sets that have been constructed from Common Crawl. But we also took, for example, the Norwegian Colossal Corpus, the NCC, Icelandic Gigaword, Danish Gigaword, etc. We extracted data from Reddit via push shift, and we used Eleuther's The Pile dataset, amongst others. We also did some quite extensive scraping or extracting of data. So, for example, we scraped some forums, including Flashback and Familjeliv, lots of governmental agencies. We extracted Swedish parliamentary debates from the Riksdagen, etc. And we also asked one particular instance, we asked FAS to be able to get their data from an API. And actually quite a lot of governmental agencies have told us after the fact that, hey, why didn't you ask us instead of scraping our data? That was rude of you, but we did what we did. So, in essence, we ended up with 1.5 terabytes of data. This is kind of a list of all of the various data sources structured around particular categories. So we have these articles, we have books, we have code, we have conversational data, we have some generated math data sets, some miscellaneous task-driven data sets. So there we have, for example, translation in Opus, natural instructions, movie scripts, summarization from another data set. The large chunk of it is probably from the Common Crawl data sets, and then some, the web sources, the scraping that does not go into the conversational data. And of course, we also used Wikipedia. So after we have these 1.5 terabytes of data, I mean, some of these are semi-structured data. You can think of all of these, like scraped Flashback, for example, that just consists of large amounts of HTML. Some of it is structured data in the, for example, Opus, which is a parallel corpus. So we kind of needed to decide, well, first of all, in some instances, like Flashback and Familjeliv, because that data is, it's quite a lot of what I would call high quality data. We made a focused effort to convert this HTML into some form of structured data so that you could get actual conversations out of it. And then when we had done that, we kind of devised various schemes to go from structured data into raw text. So large language models, they operate on just text sequences. Of course, you can put in JSON. That's a structured format that just exists in a text-based form. You can put that into a language model. We did not. We tried to take the structured data and format it as running text. So, for example, we took all of the forum pages in Flashback. We ordered them according to threads, extract user and post, and then unroll this, so we get this whole big chunk of text that just encapsulates the whole thread. And in this, we also did anonymization. So we had simple regular expression matching on usernames to kind of flip them around and not model users on Flashback, because we didn't want to do that. We also did some the extract conversations. So this is both pertaining to Reddit. The Reddit data, if you're familiar with Reddit, it has this kind of tree structure. So it's not really clear how you would go from that tree structure to just linear text. So what we did there was kind of sampled paths in this tree so that we get some kind of conversation. And with Flashback, we actually did a similar thing, but well, we did partially just use the Flashback thread. Boom, that is used that as text, but we also extracted conversations based on people quoting each other on Flashback. And for the parallel text with translation, we had a bunch of different like translation prompts or templates. So like if we had parallel text in English and Danish, we would kind of generate a translation example from a multiple or like a very large sample space. So like, oh, translate this Danish text to English, please, or this is a text in English, translate it to Danish, or vice versa. So like we tried to, and this was all an effort to like, well, if we are going to format the data, we want to have some kind of stochastic formatting so that we don't end up with a data set that is very, very driven by our fairly arbitrary choices. I mean, if we make it stochastic, it's still arbitrary, but it's even, yeah, we have some kind of variation at least. So yeah, that was a fairly substantial effort. When we had done that, I mean, we took all of these various corpora, we took the semi-structured data, transformed it into raw text in various different ways. Were all of these pre-processing steps. So this includes like normalization. If you worked with Unicode, you know that, well, there are multiple ways to encode the same character. So we kind of do like Unicode normalization, white space normalization, and remove non-printing characters from the data and stuff like that. This is just regular data processing things. And after we've done all of that, we also did extensive filtering and deduplication of the data. So first of all, we did initial quality filtering. And this is, you take one document like in isolation, and you apply, in our case, 16 different filters. And these were based on Gopher and Roots. There are articles that talk extensively about these kinds of quality filtering. These kind of filters, like in a certain document, we want 80% of words to contain alphabetical characters, for example. So, or you don't want documents that have like where 50% of the lines are repetitions, So a bunch of these fairly rudimentary but quite efficient quality heuristics. So we applied these. We also did exact deduplication over the entire data set, making sure that we did not have duplicate documents, and fuzzy deduplication, which essentially makes sure that you don't have documents that are very similar. So this whole process, I mean, like we collect data, we have some original data, we run the quality filters, we do exact deduplication on all of the data. Kind of fuzzy deduplication is much more compute intensive, so we kind of need to do it in batch. So we batch them into like similar data sets. So yeah, and then when we had done all of that, we kind of merged them into like this final data set that we used. So out of the 1.5 terabytes that we had collected, the quality filter removed like 240 gigabytes. After that, we did the exact deduplication, removed another 50 so gigabytes. And then the fuzzy deduplication on top of that removed about 100 gigabytes. So we ended up with this final data set of 1.2 terabytes. And if you look at the language and the like category distribution of this data set, you see that it is predominantly in English. 40% of the data was in English. There's a quite sizable amount of Swedish, Danish and Norwegian, and fairly little Icelandic. And also, if you look at the kind of category distribution across this, you also see that there's quite a wide range of different categories mixed between like the conversation and the codes, the books, the articles, etc. This is also just an image of of the data set as it is distributed. So here you have all of the various different sources, so like Common Crawl, MC4, Oscar, etc. So when we had done this, we kind of end up with this final data set. And when you do model training, you usually want to weigh your data set in various ways. This is a fairly arbitrary process as well, if I'm to be honest. Essentially, if you have some data set that you consider be lower quality than others, or if you have data sets that you consider higher quality, you probably want to over-represent the high quality data in your training and under-represent the low quality data in your training. And further aspect for us was that we did not want it to be predominantly English, so we applied even more extensive, like underrepresenting of English data. And then based on these weightings of the data, we sampled some data from it and used that the training data both for the tokenizer and for the model. So in the end, what we ended up with is this about 300 billion token data set, which is here. And if you look at GPT-3, they have slightly more, but comparable size. So yeah, as I said, the Nordic pile, it's about 1.3 terabytes. The actual amount we used for model training is about 300 billion tokens, or 400 gigabytes. Out of that, we sampled a fairly small fraction that we used for tokenizer training. And we used one tokenizer for all of we didn't do anything special. We just trained one tokenizer for all of the data. So it's a tokenizer that should be able to handle all like Icelandic, Norwegian, Danish, etc. And the final weighted dataset distribution looks kind of like this, or looks like this. So we have 36% Swedish, 24.5% English, etc. And probably because we are Swedish and have much further insight into the Swedish data landscape, kind of made a much more focused effort on Swedish data sources. We can kind of see that we have kind of a nice distribution of various domains for the Swedish data. That is not necessarily the case for the other Nordic languages. But yeah. So now we have all of this data, we have tokenizer, we have tokenized the data, etc., etc. It's onto the training. And when we talk about training these scales of language models, it's kind of important to think about what it actually entails. If you look here, like the model flops per batch and the total model flops, these are calculations that are just based on the transformer architecture, using the various hyperparameters and the number of samples that you want to train for. You can get a fairly tight lower bound on the number of flops that is required to actually train this model on that number of samples. And so for the largest model, the 40B model that we trained, it's about, 90 zetaflops. So for comparison, that would be about slightly over 9 years of peak throughut of an A100 card. And an A100 card, that's a fairly high-end GPU. So we needed resources to do this. But luckily, we had resources, or NSC, the National Supercomputer Center, had resources. So Berzelius, which was a donation from Wallenberg Foundation, I think, to the National Supercomputer Center. It's an NVIDIA SuperPod with 60 A100 nodes, where each node has 8 GPUs, and each GPU has 40 gigabytes of RAM, etc., etc. So, if we take that 9.5 years and divide it by our number of GPUs, we would kind of hopefully get in a reasonable amount of time. And we also had, and well, given that we had access to this supercomputer, we actually got a reservation consisting of 20 nodes. So that is 160 GPUs. If you could achieve peak throughput on on those nodes, you could be done in like 20 days for this model. I mean, that's not feasible. It's not something you can do. Utilization is not 100% for these kinds of things. But since we want to be, efficient, we decided to use the NeMo Megatron framework. And this is essentially, I mean, it's a framework for training large language models developed by NVIDIA for NVIDIA hardware. I mean, so it was perfect. I mean, we had Berzelius, it's an NVIDIA SuperPod. We have NeMo Megatron, which is a framework for training large language models. We want to train large language models. And furthermore, we had like great help and support from NVIDIA, in particular Zenodia, that Magnus mentioned. And NeMo Megatron is essentially a framework that makes it quite simple to deal with all of the complexities of doing this like large-scale model training. So if you take, for example, a 40 billion parameter model, if you train it with 16-bit floats, that's 80 gigabytes. Each of these GPUs only have 40 gigabytes of data. So, I mean, and the 80 gigabytes, that's just the parameters of the model. When you're training, you need to keep track of lots more. So, I mean, quite quickly you run into, I mean, by raw necessity, you kind of need to be able to distribute these models. You need to be able to distribute them efficiently, and like all of the scaffolding to make this run needs to be there. And well, frankly, it's not something we could do in like, in the time frame, or it's not something I would want to do, even if I could. So yeah, we used NeMo Megatron. And using NeMo Megatron, like all of these, like setting up the model training, deciding on like, okay, which kind of parallelization should we do, given that we have these amounts of nodes, these amounts of devices, this amount of memory, yada, 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 essentially boils down to like writing a configuration. You say like, I want to train a model with these hyperparameters, like these sizes, this number of layers, these dimensions, and I want it to be like, have this tensor parallelism, this kind of pipeline parallelism, etc. So that was extremely nice. Yeah, and like using the NeMo Megatron framework, we actually managed to achieve quite good utilization on Berzelius. So like the boldface guys here, that's our runs. So the 40 billion model achieved about 40% of like peak theoretical utilization. And if you compare that to the non-bold-faced ones are from NVIDIA's own articles reporting on like NeMo Megatron and what kind of utilization they get. So we kind of get comparable utilization, which is very, very good. And then that means that we're actually using this wonderful resource efficiently. So yeah. And kind of like if we look at how it went, you can kind of see for all models, first of all, the larger the model size, the better. We get a better validation loss and kind of see what we would expect. Like the 40 billion model is quite significantly better than the 20 billion model, etc., etc. And kind of like the takeaways I would take was that Berzelius was actually incredibly stable. I mean, before we went into this, we had some kind of hesitation, and people at Berzelius had hesitation that like running these kinds of large-scale jobs on this many nodes, the risk of failure of one node is quite high. And so far, we only encountered like 2 node failures, which is very, very good. And also what kind of happens, or what often happens when you train these large-scale models is that you encounter, for various reasons, sometimes during training, your loss diverges and your model kind of begins spiraling out of control in terms of performance. validation performance. And we didn't experience anything like this. I mean, occasionally we had these like loss spikes, but none that were persistent or like significantly changed the convergence of the model. So that was very nice. And Nemo Megatron simplified the training process immensely. So yeah. And well, while we were training, Felix Stollenberg, who's not here, did like simultaneously and in parallel did quite a substantial amount of scaling experiments. And well, I'm really not an expert on scaling laws or scaling, but as I understand it, this is mainly about the relationship between modeling choices, such as model size, learning rate, batch size, etc., data size, your loss, and compute. So like using the framework of scaling laws, you can kind of answer questions like, okay, so if I have a compute budget, if I have a setaflop, which model should I train to get the lowest loss? And I mean, from our perspective, that is interesting. Like if you want to push state of the art, if you want to train a model and say, hey, we got the lowest loss. But from a usage perspective, I don't know how useful that actually is. If I could spend 100 times the amount of compute training a super small model that would achieve the same validation loss as a super big model, that super small model could be very useful for future use. And this is not really something that scaling laws is about. But scaling laws is very good for like validation and sanity checking, because you can kind of predict. So like, okay, given that we have seen these kinds of losses before, if we train a larger model, what is the expectation? Like, where do we think this model will end up? So if you're doing something wrong, or like if you have kind of like hit the peak based on your data size, you would kind of see that using scaling laws. And I mean, this helped us when we initially had not really thought super clearly about how our learning rate scheduler should work in terms of the data size and the batch size, etc. And using these kinds of like scaling laws arguments, we could kind of figure out like, maybe we're actually doing something wrong here, and adjusted that accordingly. So this is also something that's very nice to have. Okay. And so once we have these models, I mean, we've trained them, we've done scaling laws, we predicted that like, okay, yeah, they are as we expect, they perform as expected, etc. How to actually use them or run inference on them. And as I've said before, 40 billion parameters, our largest model, that is quite a lot. It's 80 gigabytes, 7 billion float 16 models, that's 14 gigabytes. Apart from that, I mean, like, yeah, when you run, apart from that, you have like the running state of the model. So you need to keep track of at least the most recent activations. And you would also probably want to have a key value cache, so that like when you, but not only do you need a lot of like RAM or memory to be able to use these models, you also need a lot of compute, obviously. And well, yeah, I mean, it's not at all in the vicinity of actually training the models, but you still, I mean, like, so this is an like approximate like flop calculation per token that your model is generating. So like the largest model is in like the 80s of gigaflops required to actually like predict one token. And if we can look at what that would entail on like if you have an like, again, like I'm only talking about peak utilization. These are not numbers that you will even come close to in actuality. But if you take like AMD Ryzen like something CPU, you would, if you somehow magically manage to actually use every single flop that CPU can get out, you would get 22 tokens per second. Whereas if you use like an A100, you will get 4,000 tokens per second. And like in actuality, I think the true number for CPUs is probably closer to 1 token per second. So like if you have large documents, you really, really want to have proper hardware to run inference on these models. So yeah, and we kind of have like internally, I mean, just to give some kind of perspective, we have developed some test API where we serve GPT-3, try to more or less emulate the way OpenAI serves their GPT models, same kind of API, etc. Regrettably not public. We are going to make the code public eventually, and but the API is not public, frankly, because we do not have the computation and resources to serve many requests. But yeah, the 40 billion model, like one model instance runs on 3 A100 40 gigabyte GPUs. And the 20 billion model runs in 2. And the rest of the models are fairly small, so they can run in 1 or like a fraction of 1. But so the bad news is that you kind of need to have these resources if you're running these kinds of models. The good news is that, well, if you have it, it's actually fairly quick. If you're not under heavy load, and yeah, we are currently using it internally for evaluation, and also externally in the validation project. And I see that we have some partners here from that project. And this is the point where I hand over to Ariel. And
so let's talk about evaluation and more. And I really want to emphasize from what Amaru has been speaking of, like all parts is kind of hard, but the most work-intensive part is the data collection. So if you want to do big-scale ML, then you really should allocate time and resources for data collection. There is a kind of thing there now. But now we have some models. So the question is, how do we evaluate them? And we have taken a multifaceted approach in the sense that we have the validation project with the goal of just seeing if the models are actually useful in applications. And in this project that is financed by Vinnova, we have a couple of partners from governmental agencies to startups and the companies and even hospitals. And here the goal is to educate on like how do you actually use this model. We have written a handbook for prompting, and we also want to try to provide access to the models, to the bigger models for partners that doesn't have the infrastructure to run them, because that is also important information if people should get the infrastructure to do this. And of course, we also share the model weights. And we have already gotten some feedback from this, where one of the partners says, like, it's not as good as GPT-3, which is not super surprising, actually. But that's also a case where they want to do something really close to a production environment, where they want to create short texts from certain information. And I think our model is not as good as following instructions as the GPT-3 models. But we also make the models for the case of evaluation, and just the whole goal of the project is to make the models available. So right now you can apply for access to the models and get access to a Hugging phase where you can download these models. And soon we hope to release them fully open source. And what we have seen in the community, machine learning and AI community out there, is that open source artifacts really seem to take get a life of their own. I'm thinking of Stable Diffusion, where people really has built a lot of applications on top of this. So once we have it fully open source, people can fine tune and try to build applications with the models if they want. We have also done extensive qualitative evaluation, and this is just like my gut feeling of how the models perform. It's kind of good at generating Swedish. I would say probably the best Swedish model. But it's a bit moody when it comes to following instructions. And that is kind of expected from the way that we train the model. So what we have done is that we have taken a lot of text from the internet, and then we have tried to predict the next most probable word from that text. And what happens then is that we model a lot of conversations between humans. And then in those conversations, people might ask someone to perform an action. And the most probable answer is, yeah, I can do that. But if you have used ChatGPT, you will get kind of annoyed by that answer. You would much rather have the model actually write out the thing to you, right? But we haven't trained on that. So zero and few shot works, and it works better the larger the model is. And that means that you, I mean, the model has some kind of general capabilities. You can give instructions in text. You don't need to fine-tune the model. And sometimes even the smaller models can surprise with their capabilities in the right context. And I will come back to what I'm thinking of there. And some things that we made during the data collection process were really good. Spending time on data cleaning, I think, is extremely important to get high quality models. It seems like adding code is probably also beneficial. Some things that we did is probably not so good. So I looked at the data again recently and found out that I was when I formatted a certain data set. So it was not at all as I remembered it. And that's, I mean, just something you could improve on. And great, we have had great work from Judith and Catherine, who is in the NLU team, where they have done some proper quantitative evaluations of the model. And zero-shot evaluation is where you only have the instruction and you expect the model to complete the instruction without any examples. So here, our frame of reference is the Open GPT-NeoX model from Eleuther AI. And you can see that our 40B model is potentially a little bit better or on par with the 20B model. But we have some important notes with regards to this. Evaluation is ongoing. The way you evaluate these large language models now, industry standard is that like you do 1,000 tests, which is...
Ariel, sorry, can you repeat the important notes you just broke?
Yeah. I haven't even come to them, so you won't miss anything. So you should spend a sizable amount of time on evaluation. That's the main point, and we're currently working on it. Our model is a multilingual model. That means that it's trained on less English than the GPT-NeoX model that is only trained on English. And we might also have cheated that in the sense that some of the data sets, the training data from the data evaluation sets are in the training data. We don't think that the evaluation data is in the training data, but still that might make our model more favorable in this comparison. We have also done 5-shot evaluation. And I don't know if it holds, but the models were a little bit worse on 5-shot evaluation, which is really surprising. They should often, when you provide more context, they perform better. Yeah, we take questions afterwards, I think, if you remember.
Just 0-shot and 5-shot.
Yeah.
It's like just an extraction, and then 5-shot is 5 examples, and then...
Yes, exactly. So the 0-shot evaluation, you just have a instruction and some task that the model should solve. That's it. In the 5-shot, you have 5 examples with correct solutions before for a specific task. And these are a couple of tasks, but we will evaluate on a lot more of tasks. And part of the evaluation of this model and the surprising capabilities is that one of our smaller models, the 6.7D model, was part of an exhibition at the Liljevalchs Museum for the Nobel Prize Foundation. And there we made a chatbot with some prompting that worked surprisingly well. I don't think it was really good at writing emails, but it liked philosophizing about life. And it was a work by Alice Heyman, who was still going to gymnasiet when she did this work, and she made a really good prompting manual. And this is the proper way to interact with these models, to see it as kind of natural language programming. So with that in mind, I was really actually surprised by the capabilities of the model. So there is no clear answer. Our model is exactly as good as this model because we haven't done it yet, but the overall impression is that it's working quite well. And but we have some developments in the field as well. So I'll start to position our model, and in Europe it is the largest open model that has been developed, the 40 billion one. We even had some comments when we released it from a Danish person who thought maybe he should have born on the other side of the Öresunds bridge. So that was really fun. So what we have done is large language model pre-training. We have done it on billions of tokens and billions of parameters, and we have done it multilingual. But the developments in the field is, there's a lot more going on. So we have seen that it's beneficial to train large language models on trillions of tokens and with 500 billion parameters. So we're not quite there yet. And in addition to the pre-training that we have done, where we predict the next word, has come other ways of making the models more useful. For example, instruction fine-tuning, where you really try to make the model not answer, yes, I can do that, but actually write out the thing you want. And then we have reinforcement learning with human feedback, or reinforcement learning with AI feedback, which is a different training paradigm in order to make the model behave more in line with the data that you train on in that setting. We have full multilinguality, all the languages in the world. And there also seems to be a trend where if you have a model that is predominantly English, but it's trained on really a lot of data and it's a big model, then it kind of generalizes quite well with respect to the ability of performing tasks to languages that was not as prevalent in the training corpora. Then we also have the chat models, and the chat models are, if we're referring to the OpenAI one, they are both instruction fine-tuned, and on top of that, they are also trained with reinforcement learning with human feedback, and they have also formatted the specific chat fine-tuning data in a certain format that is more suitable for chat. So they have done a lot of extra work in pre-processing the data only for chat. And that makes sense, I guess, if you want to build a product or if you really know that you want to build a chat model. And then we have multimodality. So why not throw everything into a single transformer? Let's put in images and sound and actions and so on. And we see that at least multimodality with respect to images has recently come out. So yeah, we're also part of a thriving international open source research and application ecosystem. So things are really happening right now. There's a lot of communities on Discord and on the internet. It's a Luther, we have Hugging Face, we have Carper, Lion, and of course AI Nordics, which you all should join if you're not there. And we have open source tools to like really make language models more useful, such as LangChain, where you can kind of, with these tools, very easily combine web search and database lookups and such things with language models, such as GPT-SW3 or any one that you can find on Hugging Face. We have Llama Index, which is a special framework for just querying vector databases and putting the results back into the language models. So things are really going on, and some of these communities, it's a bit unclear if they're like fully open source or if they're companies or if they're where they're getting their finance from, but whatever, it's open. But we have also seen some interesting changes recently. So I think we're actually entering kind of a, I mean, this has been implicit for a long time, but more explicit race dynamics towards potentially AGI, or at least taking a big part of the market with respect to novel AI technologies. So OpenAI released GPT-4 yesterday. And together with the GPT-4 model, they also released a technical report. They didn't release a paper. And the specific part of that technical report says, given both the competitive landscape and the safety implications of large-scale models like GPT-4, this report contains no further details about the architecture, including model size, hardware, training, compute, dataset construction, training method, or similar. So the race is going on. And together with that, of course, very capable models. And what these companies are doing are, as Magnus have pointed out also, really, really big projects. So CERN, I think you all know what that is, like the big particle accelerator that we dug into the ground in Switzerland, among other places. It costed $5 billion US, and the latest round that OpenAI got was $10 billion. And this is the author list from the technical report, all people that were involved in training GPT-4, and that's almost 3 A4 pages with really small text. So there's a lot of people, and that kind of hints towards the effort that needs to be put into building this kind of models. But we also have new opportunities with respect to the work we are doing. So if you want to use large language models such as GPT-SW3 in-house, if you're a governmental agency or some other company, then I recommend checking out these new commercial large language models for data annotation, because they're really good at some things. But if you want to do anonymization, for example, why not use them for creating really cheap, compared to hiring humans, annotation data, and then fine-tuning your in-house model. So, I mean, it's quite exciting, I think. AI and language technology is a field that is moving really, really fast right now. And I love this meme because I can relate to it a lot. What a week, Captain, it's Wednesday. But I think really, here comes a little brasklapp. I think we need to realize in Sweden and in Europe that if we want to be part of this, we need to have bigger projects and bigger efforts and collaborations, because it's not feasible for a small ragtag team like us to produce something like GPT-4. Although we can do great contributions, we can do research, but the investment is just not comparable in a sense. But with that said, we are still part of the journey, and I think we're building great tools, and we have been quite a big team. So yeah, thank you. Let's go to the questions.